which is proportional to our likelihood times our prior. Okay, so a really popular method to sample from the posterior distribution is Markov chain Monte Carlo. So the idea behind that is to construct an ergodic Markov chain that has our posterior as the invariant distribution. And this package and this talk is going to be focusing particularly on Metropolis Tastin's MCMC. So that's where we make some proposal with some proposal distribution Q, and we accept it with this probability here. So that's Metropolis Tastin's MCMC, and you can see that it does involve the likelihood. So as I'm sure all of us know since we're in this session, the likelihood's not always going to be tractable, or it might not be available in closed form, or it could be too expensive. And so that motivates likelihood-free methods where your likelihood function is intractable, but you can actually simulate data from your model. So I'm going to call in general simulated data X, and the simulated data for our, the summary statistics for our observed data are going to be denoted as Y. So we could work with a full data set, but often we're going to reduce our data to a set of summary statistics, and that's what we're doing here. So then the objective is to sample from the summary statistic posterior, which is proportional to the summary statistic likelihood times the prior. And we're going to avoid computation of both of these things. So since the likelihood is typically intractable, typically so is the summary statistic likelihood. Okay, so there's two methods that I'm going to be speaking about. The package is focused on the second one. So the main method that a lot of people use, that is the name of this conference, is approximate Bayesian computation, which is a non-parametric approach. And I'll also be talking about BSL. Okay, so ABC is the current state-of-the-art likelihood-free method, and it compares the simulated and observed summary statistics using non-parametric methods. Through this, for anyone who may not be familiar with it, a basic method is that you simulate NIID data sets from the model based on theta. You calculate the associated summary statistics, and then in your MCMC or your algorithm, you replace your summary statistic likelihood with this estimated ABC likelihood. So this involves a discrepancy function, which gives you a measure of distance between your simulated and observed summary statistics. For example, the Euclidean distance. It involves a kernel weighting function, which has some bandwidth epsilon, and you tune your epsilon to hopefully go towards 0. Okay, so that's the non-parametric version, but unfortunately some problems with that is that it's highly sensitive to the choice of tuning parameter epsilon, to your discrepancy function, and to a lesser extent the kernel weighting function. And unfortunately there's no standard way to select epsilon or rho. Okay, it also suffers from the curse of dimensionality with respect to the size of the summary statistic. So that kind of motivates a parametric alternative. It might be possible to overcome some of these drawbacks using a parametric approximation instead of the standard non-parametric approximation that's used. So the most popular parametric approximation is the synthetic likelihood. So this was introduced by Simon Wood in his 2010 paper in Nature. So basically we're just using a normal approximation to the summary statistic likelihood. So this makes sense when the summary statistics are subject to the central limit theorem and in a whole bunch of other situations. And we're going to refer to a Bayesian version of this as BSL. So I'll briefly go through how that method works, but basically this talk is about a package of BSL. Okay, so BSL, the basic idea, the structure kind of looks similar to ABC. You start by simulating NIID datasets from the model based on theta. You calculate the n sets of summary statistics, and then rather than using that non-parametric approximation, you're going to actually use this normal approximation where you've estimated your sample mean and your sample covariance from your set of simulated summary statistics. So you can put that into MCMC, and basically that's just the way you get the likelihood for a single proposal. Okay, so the benefits are that it requires less tuning than ABC. It can be more computationally efficient than ABC in certain settings, and it can more effectively utilize parallel computing architectures. Okay, so that's a bit of a background on ABC and why we might want to use BSL rather than ABC. But now I thought I'd just briefly tell you a little bit about the packages that exist already. And actually the next couple of talks are about two of these packages. So hopefully hopefully I'll do them justice. Okay, so there's a Python package ABCPy, and that's a framework for approximation computation that speeds up inference by parallelizing computation on single computers or whole clusters. That was a little byline that I found. So ABCPy is really flexible, and it can do ABC methods, and I believe a few other alternatives as well. LFI is a statistical software package for likelihood-free inference. Again, I'm not going to go into it in too much detail since it is being spoken about next. And PyABC is another Python package. But these three kind of, they're general likelihood-free ones, but they do focus a bit more on ABC, and our package is going to focus on BSL. Okay, in terms of our packages, we have ABC, we have Easy ABC, and there's also SynLick. So SynLick was by Simon Wood and Matteo Faciolo. So our package is, you can kind of think of it as extending these so that you've got some more recent advances into Bayesian synthetic likelihood. Okay, so our package is for using BSL and its extensions by just providing a function for simulating data from the model, calculating summary statistics, and evaluating the prior density. So this is something that's kind of common to all ABC and BSL type methods. And so you'll see this kind of format in a lot of software. So I'm going to start by talking about the basic usage for the BSL package. Okay, so firstly, just installing it. It's very unfortunate that we just very recently got a message from CRAN saying that another package has changed its dependency, so they've taken ours temporarily off, but it'll be up in the next few days. Okay, so unfortunately, this install.packages is temporarily down, but you can use DevTools install using the version from GitHub. Okay, and then obviously when you've got a package installed, you can use library to load that. Okay, once you've got the package loaded, the main thing is you need to set up this model object, an S4 class called model. So that's going to include, as I said, a simulation function, a summary statistic function, and things like the log prior, for example.
Yeah, okay.
The simulation function, as you might expect, is going to require you to put in your parameter value. So this simulation function is going to simulate either one or n data sets from the model based on this parameter theta that you give it. And you can also add optional additional arguments as well. Okay, the next one is a summary statistic function. So for this one, you plug in the data as the first argument. I'll go through some examples shortly. And yeah, you need some point estimates or initial values as well, as you always do for MCMC. And once you've got that model set up, you can just run this BSL function. So it's kind of a two-step procedure. You set up the model, and then you use that model in BSL function. And this BSL runs MCMC with Metropolis Tastings random walk. So I'm going to go through this toy moving average of order 2 example. So I don't think it's important to go into too many details on the model. It's just a really simple one that would run quickly enough for this talk and was relatively easy to explain. So we've got these two parameters, theta1 and theta2, and the likelihood function actually is tractable. So if you wanted to, you could compare these results to standard inference. This example is also built into the package. So if you wanted to find out more, you could do library BSL and then !ma2, and it'll bring up the help file and the examples of how to run this. You can also load the associated data and the summary statistic function and the simulation function, etc., just using this line here. Okay, so let's set up all of the parts of the model. The first part is going to be a function to simulate data. So as you can see, the first argument is our parameter theta, and then we've got this additional argument that we'll pass in separately as well. This part here is really that's just the MA2 model, so it's just based on this thing here. Okay, so this typically is the main bottleneck in expensive models. You're simulating your data is going to be the expensive part. So there's a few ways you could try and speed things up. We've got an option that you can actually make this parallelized. So in that case, you'd have your number of simulated data sets as an input as well. Or you can use, say, C++. so that you've got a function that's written in C++ in the back end for this. You also need your summary statistic. In this case, we're just going to use the raw data, so it's really simple. Our summary statistic is just you plug in the data and it gives you the data back. And we need a prior as well. So we're just going to have a uniform prior on a feasible region that's defined here. So this feasible region is the region that gives us an MA2 model that's stationary and invertible. Okay, so that's just written in here. We plug in our parameter theta, and then it gives us the log prior evaluation. So then it's pretty simple, at least we like to think, to put all of that into a new model class. So this is the way you do that. You say fnsim equals your function, fnsum, this is the other function you've defined. There were some extra arguments that were required in the simulation function, so those can be entered in here. There's the initial value, and there's the log prior function. So you can do all that, and then it will spit out that it's checked your model and everything seems to be working well. You're not missing anything. I can see that something's popping up on the chat. If there's something I need to know, can you let me know? Okay, try and fix that. Okay, so now we've set up the model, we can actually run BSL. So this is the function to run standard MCMC BSL without any adjustments. We've got some data, we've got the number of simulated data sets per parameter theta, the number of MCMC iterations, our model, and then this thing here is the covariance matrix for our random walk. And then the method is just BSL, saying that we're doing standard Bayesian synthetic likelihood. Okay, so we can then show the results for that, which is just giving us some summary information. Actually, I think this might have been based on a shorter run, so it might not be great, but you can see the kind of information you can get. This is the acceptance rate. We've got the early rejection rate, which is something related to having a constrained prior. And we can also do summary of our output result, and you can get the effective sample size for each of the parameters and the acceptance rate there as well. Okay, here's a plot. So what we're doing is we're plotting the results. This which is just saying use standard plotting rather than ggplot2. I wanted to show you the true parameter value, so that can be done through theta true, and I wanted to do some thinning as well. So this here is thinned so that we're taking every 30th sample. This second line is really just to provide a title. So you could get a simpler version of this, but by just doing plot result MA2 BSL thin equals 30. Okay, so that was a really basic test case. Now I thought I'd go through some more advanced usage, and I might need to go through some parts of this a little bit more quickly, but hopefully it'll still make sense. Okay, so limitations of BSL in no particular order are that the BSL target technically depends on the number of simulated data sets. So that's really not that big a deal. It's also the case in ABC, but it is, I guess, could be considered a limitation. The distribution of the summary statistic should be roughly normal because we are using that normal approximation. The model can perform poorly when we've got misspecification in our model. Also, if you've got a high dimensional summary statistic, which you might like so that you don't lose as much information from your data, then that can be an issue as well because you need to simulate a large number of data sets in order to estimate your covariance of your summary statistics. And then finally, this package is based on MCMC BSL, which relies on MCMC to explore the parameter space. So that's not going to be ideal if you've got a high dimensional parameter. So just talking about some extensions, we've got unbiased BSL, which is a method that's theoretically unaffected by the number of simulated data sets if you've got a Gaussian summary statistic distribution. We've got some methods that help to improve in the case of non-Gaussian summary statistics. We've got some methods for model misspecification and high dimensional summary statistics. And in the future, we're going to look at this high dimensional parameter setting. Okay, so that's just kind of recapping that. Okay, and I think I might skip UBSL for time, and I'll go into the more interesting ones. Okay, so one of the more interesting ones is semi-BSL, which is for when you've got summary statistics that don't follow a normal distribution. So in that case, you might like to use a semi-parametric alternative that's kind of a balance between the parametric and the non-parametric methods. So what you do here is for each individual summary statistic dimension, you use kernel density estimation to kind of approximate that, and then you can transform those summary statistics so that they're roughly uniform distributed, and then using the quantile function. Sorry, I'll start that again. You do a KDE approximation for each of the marginals. Then you use the CDF to convert those to uniform 0, 1, and then you can use the quantile function of the normal so that each of your marginals are normally distributed. Okay, so now you've got marginals that are normally distributed, and you're going to approximate the full set of summary statistics using a multivariate normal approximation to that. Okay, so that's what this thing is doing here. It's using a Gaussian copula to model the dependent structure. Okay, so the good thing about this is that we don't actually have any additional tuning parameters, and it doesn't appear to require more model simulations than BSL. So it's also quite easy to run in our package. So you can see the only difference here is we've got method equals semi-BSL, and before we just had BSL. Okay, we've also got some models for misspecification in here, but I might just skip through that a little bit and just show you that if you're concerned about potential model misspecification, then you can handle that using method equals BSL misspec, and you can use one of two types of misspecification type. BS Lasso is a way that you can handle high dimensional summary statistics. So as I said earlier, if your summary statistic is really high dimensional, then you need to do a lot of simulated data sets in order to estimate the covariance. So what we can do is we can use some sparse approximation to the precision or the covariance matrix of those summary statistics. So the graphical lasso is one approach to do that. It enforces sparsity in the precision matrix. And the way you can interpret that is that you're implying you've got conditional independence among some summary statistics. Okay, so here's the estimator. What we have in black is just the standard estimator we use, but you can see that now we've subtracted this lambda times the L1 norm of the precision matrix. And so as we increase lambda, we're going to get more sparse precision matrices. And so that means we might be able to use fewer simulated data sets in these high dimensional settings. So again, running this is relatively simple. The rest of the code is the same, except now we've got shrinkage equals lasso for graphical lasso, and we've got a penalty. And I'll talk a little bit more in a second about how you can tune that penalty. Okay, so the penalty controls the sparsity. Higher penalty leads to more sparse approximations. And so we need to tune this value of lambda, and that's also going to depend on what our number of simulated data sets is. If we have a higher number of simulated data sets, we don't need as much sparsity. Okay, so we're going to be basically doing our tuning to aim for a standard deviation of the log likelihood of roughly 1.5. So that's based on literature saying that that can be a good approach in these contexts. And so you can do that kind of thing here. This is some methods for doing our tuning. And you can see that we've got the summary statistics of our observed data set, and we're plugging in a few different values of n into this. And for each value of n, we've got a sequence of different lambda values we might like to try. And basically what this is going to do is it's going to tell you, as you can see here, which penalty value has the lowest standard deviation of the, the best standard deviation of the log likelihood. Okay. So you can also do plots of that as well. I might skip this one. Sorry, I was a bit overambitious in the amount of context I had. This is just an alternative shrinkage method. You can see that, again, it's pretty easy to apply. So I might go through that a little bit more quickly as well, sorry. I'm going to skip straight to the toad example. So this is another example where it's an individual-based model for the movement of Fowler's toads. And the model assumes that toads take refuge during the day and they forage throughout the night. So we've got an alpha stable distribution with parameters alpha and epsilon. And so we're trying to estimate those, and we've got 48 summary statistics. So that's a little bit too high to handle for standard ABC methods. Okay, so here's how you'd run this. We've got just collecting the data from our package. Then we're setting up a new model where this is our function to simulate data. This is our summary statistics. And we've got a log prior function as well. And so basically a bunch of this is just in the data set. You'd need to do this in your own application to figure out what your summary statistics and simulate data sets are. Okay. And also here in this case, we've got a constrained, with our parameters theta are constrained, and so we can take that into account as well. And now you can see, you can quite easily run a whole bunch of methods. You can run BSL, you can run the semi-BSL method I spoke about, and you can run methods for shrinkage as well. So this is just highlighting that there's this base code for BSL, and then to run other methods, it's really quite small adjustments. So that's kind of the point of our package. You can use it to do base BSL, but more importantly, you can use it to do all of these extensions as well. Okay, here's summarizing the results. So you could look at that and get the effective sample size and the acceptance rate as well. And then you can combine all of your results. So this is just putting all of our results into a list. And then when you plot that, you can see that we've got the marginal densities here. Okay, so just to summarize, BSL is a method that has quite a few advantages in certain contexts over ABC. It requires less tuning than ABC. It's more computationally efficient in certain settings, and it can use parallel computing architectures really well. I didn't go into that due to time, but we have got the possibility for that in our package as well. And also, many of the advantages of the original BSL algorithm have been addressed, and those methods are in a package as well. So just quickly, some things that our package doesn't do is it doesn't do model selection, which I know some of the other packages that have been spoken about today do, and it doesn't do automatic summary statistic selection either. Okay, so that's it. Thank you.
Thanks, Leah. Beautiful talk. Questions from the audience?
Yes. So I have a question.
Please go ahead.
Oh, thanks. So Leah, nice talk. That's not a question actually, but nice talk. And now when you have non-Gaussian, now usually BSL relies on, say, the central limit theorem to get Gaussian Gaussian summary statistics. Now, when you convert to a copula, does everything still work nicely in terms of theory?
I'm not as familiar on the theory side of this, but you've still got some assumptions around the dependence of the parameters being Gaussian once you've done the transformation. So yeah, I'm not sure if that answers your question. I think unfortunately I can't answer your question because I don't know the theory.
Yeah, because basically, you're saying that, we're saying that the summary statistics are multivariate normal, and that's the way we do the inference. Now, I suppose turning it into a copula, you would have to check that by doing a Gaussian copula, you actually get a multivariate normal, because if you didn't get a multivariate normal, just because you do copula stuff doesn't mean that you're going to get a multivariate normal distribution for, you might get univariate normal marginals, but you won't get multivariate normal distribution. So you have to check that, I suppose, in order to legitimately apply the non-Gaussian stuff to it.
It depends on where the non-normality is. If it's in the marginals, then maybe this approach will help. If it's in the way that they're correlated, then we're not going to fix problems with that. But I should mention that that work I wasn't a co-author on that package. I was on that paper. I was talking about the package which does implement that. That paper is in here somewhere. So this one here. So that's the Wen, David, and Chris.
Okay.
There's still time for another quick question.
I have one.
Go ahead.
Thanks, Yuka. Hi, thanks so much for the nice talk and for the set of papers and the software that arise out of the BSL approach, which I use quite a bit in a few papers. So I'm really, I like the methodology. There is just something that I'm not really super sure about. When we talk about ABC basically being unable to tackle this sort of large dimensional summaries, where large, of course, it's a bit arbitrary. You mentioned at some point in your slides that, okay, we have this example with 40 summary statistics, and this should be challenging for ABC. Now, I understand that if you use an ABC MCMC approach, that's certainly true, because it's difficult to scale the summary statistics appropriately. But if we frame the problem within a sequential Monte Carlo ABC, I've actually managed to deal with, for example, that cell motility and proliferation example that you have in your BSL paper, which has 145 summaries. And if at each iteration of sequential Monte Carlo ABC, you have many summaries for each parameter particle, which you can use to, at each iteration, rescale the summary statistics online. And there is a paper also by Chris and Chris Durandi and Halamadi and others that do that. So I actually managed to obtain the same precision as BSL with 145 summary statistics applied to the same example that you have in your paper. So for this kind of dimensions, actually ABC can be used. And I wonder what are your, maybe not thousands of summaries. What are your thoughts on this?
Good that SMC ABC can do that. I guess I'm mainly talking about MCMC.
Sorry, it seems like we have lost the sound from the Australian.
Can you hear me now?
Yeah.
Okay. So I don't know where it cut off. Basically, I was saying that there might be improvements of BSL that would help as well. I do think that in general, the non-parametric approximation can be an issue in really high dimensions, and tuning's an issue. But I'm not saying that, BSL is always going to be better. It sounds like you found a good way to handle high dimensional summary statistics with ABC, but I still think this has a place in the toolbox. Thank you for the question.